Okay, so welcome back, and so today is the last lecture on singular perturbations and boundary layers. And let me just recall what we saw yesterday rapidly. So yesterday we considered, we introduced the penalization method for Dirichlet boundary conditions, and we proved the convergence of the method using a boundary layer approach. So let me just give you a reference for what we saw yesterday. So in this book of Boyer-Fabry, so called Mathematical Models Tools for the Study of incompressible Navier-Stokes equations and related models. So in this book there is a chapter on modeling of boundary conditions through a penalty method, and so there is the details for Dirichlet boundary conditions. So through a penalty method for Navier-Stokes equation. So there is a chapter on this penalization method for Navier-Stokes equation and using the boundary approach. And so what I presented yesterday was following the same approach for a simpler model, which was just a reaction, a diffusion equation in dimension 1. Here they consider high dimensions, okay? Well, it's 2 or 3 in this book. And today, so what I would like to consider, so in this book, they only treated the Dirichlet boundary conditions. And so what we are going to see today is Neumann or Robin boundary conditions. Okay, which are, let's say, less studied in the literature, okay? So we want to do the same, to suggest a penalization method for this type of boundary conditions. So imagine we have a domain, as yesterday, big U. This is the initial problem. And here we will consider that we have an equation with the Neumann or Robin boundary conditions on the boundary. Okay, so let's consider this equation minus Laplacian U plus U equal F in big U, and then we will consider Neumann boundary conditions or Robin boundary conditions. So the general form is normal derivative, which I will write this way: du scalar product with the normal vector, okay, which I'll call n tilde plus alpha u equal j tilde, and j tilde is some data on the boundary. So this is, let's say, our initial problem with the Neumann or Robin boundary conditions, and we want to suggest a penalization method. So instead of solving this problem, we are going to replace it by a penalized problem by immersing this domain in a bigger domain, big omega. And so just by analogy with what we did for Dirichlet boundary conditions, so remember for Dirichlet boundary conditions we introduced a forcing term of the form chi over epsilon u in the equation, because we wanted to impose u equal 0 on the boundary. So here, just by analogy with that, what we are going to do is we are going to add a forcing term and we want to impose this boundary condition, so we are going just to introduce the boundary conditions in a volumetric way in the equation. So how we do that? So we are going to solve minus Laplacian u epsilon plus u epsilon, and then we are going to add a force like chi over epsilon. So chi, it's always, again, here it's the characteristic function of small omega, which was the complementary domain big omega minus u bar. And I am going just to introduce this boundary condition in this way. So gradient u n plus alpha u minus g equal 1 minus chi f. This will be an equation in big omega. And let's say we are going to put simpler boundary conditions. So we are going just to take u epsilon equals 0 on the boundary. Okay, so this is the penalized problem in this case. So we have u epsilon everywhere. And so here, because that's why I called the normal vector n tilde and j tilde, these are defined only on the boundary. But here in our penalized problems, we need n and j and g to be defined in the complementary domain, small omega. So here n will be a lifting of n tilde. We need to extend n tilde inside omega. So let's say we are able to extend it, lifting of n tilde in small omega with the complementary domain, and g is also a lifting of the boundary data in small omega. So this is, let's say, for the moment, just formally what we suggest as a penalization method for Neumann and Robin boundary conditions. And we are going to consider the same questions as yesterday. The question is, we want to prove that u epsilon, the solution of the penalized problem, converge to the solution of the initial problem in the initial domain. And also we want to be able to have an estimate of the error with respect to epsilon. Okay, so this is the program for today. And we are going to start with a one-dimensional case, as yesterday. So in one dimensions, so in one dimension, we suggest, for instance, to work, we are going to take this initial problem. Okay, so the initial domain is 1, 2. And we have this equation. And so here we are going just to concentrate, as yesterday, on one boundary. So we are going to put Robin or Neumann boundary conditions on the boundary 1. But then we are going just to take Dirichlet on 2. Okay, so we are going just to concentrate on this boundary. Here we have Neumann or Robin boundary condition, and then we are going to put on Dirichlet boundary condition. And the equation, let's say, it's minus u double prime plus u equal f in this domain. And our boundary condition is this one. Okay. So what I wrote here, if we want to write it in the one-dimensional case, so it's this equation. The boundary condition is minus u prime plus alpha u equal j1 at point 1. So all this is at point 1. And so the penalized problem is, okay, I'm gonna maybe write it just one time, penalized problem So for the Planck's problem, we are going to add a fictitious domain. So we are going just to add the 0, 1. The fictitious domain will be 0, 2. This will be big omega. Omega is 0, 2. And so the equation, let me write it maybe once. So it will be minus u epsilon double prime plus q epsilon plus, this is chi equal 1 in this part. Chi over epsilon, our boundary conditions that we will introduce in inside this small omega. And so it will be like that, u epsilon prime alpha u epsilon minus. So here the boundary data is G1. We can just extend it by a constant, so we will have here G1. So in one dimension, it's easy to extend some boundary on the data on the whole domain, and so this is 1 minus chi f. So all this is in 0 in the big omega. And on the boundary, we are going to take Dirichlet on 0 as well. So we will have Dirichlet boundary conditions on 0 and 2. Okay, so this is the equation. So let me first, before maybe starting the analysis and the boundary layer approach in this case, comment on some points here. So formally, let's look at what happens formally. So formally, when, as we did yesterday, when chi is 0, so which means when we are in the initial domain, then we recover our equation, our initial equation. This is in U. And when we are in the obstacle, so we are going still to talk about the obstacle domain and let's say a fluid domain. When chi equal 1, again, as yesterday, we are expecting, so this term will be dominant, and so this will impose this equal to 0 in the obstacle domain. And so okay, we will have this equation that will be satisfied in the obstacle domain. And if we assume that that at the limit, let's say at the limit, the solution is continuous and even the derivatives also are continuous, then if this is verified here by continuity of u epsilon and u epsilon prime, this will also be satisfied on the boundary, I mean on the right part. And this is exactly what we want to impose as boundary conditions at point 1. Okay? Okay, so, so which means that the difference with yesterday, if we want to recover our initial problem, we need to have, so we need the limit solution u0 to be C1. Okay, we need to, yesterday we saw that the limit solution had some jump on the derivative at the interface. Here, if we want this to work, we need to have u0, let's say, and u0 prime continuous at x equal 1. Okay. Otherwise, this will not work. So let me just comment on that. So if we need this to be continuous, it means that we don't want a boundary layer. Okay? We don't want a boundary layer at this interface. Okay. So because if there is a boundary layer, it's to correct, for instance, the jump in the derivative, and we don't want a boundary layer here. And this will explain the signs here. So if we just look at what happens on the obstacle domain, I put chi equal 1. this is, if you multiply everything by epsilon, this is a convection diffusion equation. Okay, there are reaction terms as well, but okay, let's look just at the convection diffusion. As you have, it's of the form minus u epsilon double prime minus epsilon double prime u epsilon double prime minus 1 minus u epsilon prime. This is a convection diffusion plus other terms, but let's focus just on that. This is a convection diffusion equation. And we saw in the first lectures that when we have a minus sign here, remember, I think we took this example in the first lectures. When there is a minus sign, we had a boundary layer at the left boundary. And we can show it was by studying the boundary layer. And if we take plus, then we will have a boundary layer at point 1. So here we have the good sign, because imagine we had only this equation here. When we have these signs, the boundary layer for the limit solution was on the left part. And this is what we want here. We don't want a boundary layer to be on the right part. Okay? Okay, so now I will maybe comment on the PDF directly. So this is our problem. This is our initial, this is our penalized problem, and as yesterday, we can split it into a problem in the obstacle and a problem in the fluid domain with the transmission conditions at the interface, which is 1. And we can show, so here in one dimension, we can show that there is the existence and uniqueness of the solution of the penalized problem. So this is maybe the first step before looking at the convergence, is showing that the penalized problem is well posed. And here we don't have, there is a lack of coercivity, so we cannot use Lax-Milgram, but we can, for instance, by in the one-dimensional case, by splitting the problem, we can solve it explicitly and show that there is existence and uniqueness. So this was an article that we, for instance, in a previous article, okay, sorry for that. So in a previous article, we studied the one-dimensional case by solving explicitly and then taking the asymptotics. You can look at this, and there is the existence and uniqueness of the solution. So here what we suggest is to use a boundary layer approach to show the convergence of the penalization method. And so what we do, as yesterday, and as I try to explain here, we expect to have a boundary layer only at 0. Okay, so this is the ansatz we are going to take for the solution. In the fluid domain, there will not be a boundary layer. So as yesterday, we have a development just with the variable x. We have this asymptotic expansion in powers of epsilon. And in the fluid domain, we are going to assume this expansion. We will have a dependence on x and a dependence on the boundary layer variable, which will be the distance to 0 over the thickness of the boundary layer. And for convection diffusion equation, we saw that the thickness was epsilon. Okay, so that's why here, if we take, we don't take epsilon squared, so we take just epsilon, the thickness for convection diffusion equation, when we have minus epsilon here, was of order epsilon. And so the stretched variable is x over epsilon, because we will have a boundary layer near the left boundary. Okay, so this is the same as yesterday. Well, yesterday we had a boundary at 1. Okay, that's why yesterday I took -1, 0, just to simplify the calculations. We choose 0 to be the region of the boundary layer. We assume again that there is an outer part and a part related to boundary layer that we will localize afterwards. Okay, and so then what we do is essentially the same thing. We take this ansatz, we introduce it in the equation. We have this formula for the derivative. If we have a function that depends on two variables x and z, then w x over epsilon satisfies these formulas as yesterday. And this is what we do. We take the different equations. So this equation, the first equation that we take is the equation on the obstacle domain. And we identify the terms corresponding to the powers of epsilon. And this will lead to different equations on W0, etc. We use the fact that W tilde goes to 0 when Z goes to infinity, and we obtain different equations, okay? So this is the equation on W0 bar. Okay, etc. By difference, we get the equation on W0 bar, okay? We look at the different orders with respect to epsilon. So you have to be very patient when you do these calculations in order not to make mistakes. And then we look at the equation on the free domain. This is simpler because there is no boundary layer term, so we end up just with simpler equations. Then we look at the equation and at the transmission conditions at x equal to 1, and these also will be simple because we don't have boundary layer. Okay, we assume that the boundary layer is localized at 0, so here we will have continuity of the different terms and the continuity of the derivative as well. And finally, we look at the boundary conditions at 2 and at 0. So at 2, this will just give us that V0 will be 0 at this endpoint. And regarding the obstacle, because there is a boundary layer here, we will have a relation between the correctors and the value, okay? Because we expect to have a boundary layer here, and so we will need to correct the error. Okay, so the limit solution will satisfy this equation, which is our first order equation. So we need to impose the boundary conditions on one of the boundaries, and this will be 1, okay, given the signs we chose. So this equation, if you impose the value at 1, this will give you some solution, and there is no reason that the value at 0 will be 0, and so you will be a corrector to. So there will be a boundary layer region here, so a region of part variation at a given epsilon. You will have here. You will need to satisfy W epsilon equal to 0, but then you have some value here, and so you will have a sharp variation here of the solution. Okay. Okay, so when we wrote the different equations, the second step is solving these equations. Okay, we have different equations that come from the different orders in epsilon, and now we are going to try to gather different equations and try to solve them. So when we starting with B0, for instance, so we have this equation minus v0 double prime plus v0 equal f. And then we also had some equation on w0 bar. So this is what we obtain. It's the limit solution in reality. So you obtain that minus w0 bar prime plus alpha w0 bar is g1. So this will be the limit solution in the obstacle. And then you have that w0 bar is equal to v0 at point 1 because there is continuity. But now you have to, so w0 bar here depends on v0 and v0 depends, we want to close the equation. So what we do is just here, if you remember, we are expecting to recover our initial problem. So our initial problem, w0 bar or v0, so the solution in the fluid domain, we expect to have minus v0 bar 1. We want v0 to be u. So we want it to satisfy the Neumann-Robin boundary conditions. So we want to v0 prime 1 plus alpha v0 1 to be g1. And how do we obtain that? It's just by writing that v0 prime from the asymptotic, from the profile determination of profiles, we find that v0 is continuous and the derivative also at point 1. So this will be equal to minus w0 prime at 1 plus alpha w0 prime, let's say bar at 1. And from the second equation, you know that w0 bar satisfies this equation in the obstacle. Okay, and so by continuity, so if everything is smooth, it will be satisfied, this will be also satisfied at point 1. So this is equal to g1. Okay, so this is how we close the equation. Sorry, I am... Okay, this is how we close this equation. So we obtain what we expect. So v0, this means that v0 is the solution of our initial problem because it satisfies the same equation, minus u double prime plus u equal f with this boundary condition at 1, and we have Dirichlet boundary conditions at point 2. And w0 prime, we obtain also what we expect. We obtain that it's a solution of this, so it's the first order equation, transport equation, and the boundary conditions is imposed at this boundary 1. Okay, and then we have an equation on w0 tilde. That was something, some derivative with respect to z. So just I come back to it. It's like yesterday, some equation of this type. And we solve it. So it will be some exponential, and taking into account that this should decrease when z go to infinity. This will just give some constant times exponential minus z. And to this constant, again, here I should, we could at the beginning so w0 tilde, we will find at the end that it will depend only on z. So we could have assumed that at the beginning, but in the high dimensional case, we need to take also the dependence on x. Okay, so here we have some boundary condition that should be satisfied, and just by extending as yesterday this boundary, we assume that it should be satisfied for all x in the obstacle domain. We find this constant w0. Okay, so we end up with something that is that resembles to like boundary layer terms, so some exponential, some decreasing exponential. And then we continue. So we have V0, we have W0 bar, and we have W0 tilde. And then we take the other equations on V1, etc. So for V1, we do the same as before. We write at the same time the equation on V1 and W bar 1. And we are able to write like equations with the fixed boundary conditions. So this is well defined, and also this one, because W0 bar was already obtained before, etc. Then we look at W tilde 1. And so the difference with yesterday we had for W tilde 1 was it was also equal to 0. Here it's not equal to 0. It's equal to some some decreasing exponential. But this is a differential equation with constant coefficients. So the solution is the general solution, and then we look for a special solution. And we find a special solution of the form z exponential minus z. In this case, and then with the boundary conditions, we are able to fix all the constants. Okay. Okay, so we continue. V2, again, same thing. We obtain the equations on V2, on W bar 2, and on W tilde 2. And we are able to solve it with the boundary conditions that we extend, let's say. Okay, so we have all our terms in the ansatz. Let me just write the ansatz we took. So so V epsilon in the fluid, we just take V0 plus epsilon V1 plus epsilon 2 V2. There is no boundary layer, and for the solution inside the obstacle, we expect a boundary layer near 0, and so it's W0 x over epsilon plus epsilon W1 x over epsilon plus epsilon square W2 x over epsilon, etc. Okay, something I didn't say yesterday is we want to show that the remaining terms are of order. We want to show a convergence at order epsilon, but here we take the asymptotics up to the order 2, because in practice, so in general, I don't know here, but so in general, sometimes we should go to the up to the order 2 in order to obtain that the remainder is of order epsilon. Okay, so if we stop just here, then we will not be able to show that this is of order epsilon, and so that's why here we go until the second order. But at the end, what we will find. So this is next step. So what we do is that here we stop here, and we say that this is epsilon some remainder, and this is another epsilon w epsilon r x. And again, okay, this was the ansatz again. In the expansion of when we have a boundary layer, what we do is that we localize. Okay, so we are going to localize the correctors with this cutoff function theta. So theta this time will be equal to 1 in a neighborhood of 0, because the boundary layer is at 0. So theta is something equal to 1, and then the support is included, for instance, in 0 and half. Okay? So this, we do that in general because we want to have exact correctors. We don't want the corrector to perturb what happens here at the interface, because we want to have the continuity here. Anyway, so this is what we do in general. We localize the correctors. So just the terms tilde are multiplied by theta. The other terms W0 bar, etc., they are defined everywhere in the obstacle domain. Okay. So this is as yesterday. Now that we found all the terms, so V0 is defined, you have its equation, etc. Also have some regularity because we are in one dimension, V1, V2, every term here is already defined. And so now we look at, for a solution in this form by introducing these remainders. These, as yesterday, just some notations. W up is an approximate solution in the obstacle domain, V up is the approximate solution in the fluid domain. And then the objective is to estimate the remainders, okay? So as yesterday, if we are able to estimate, if we show that the remainders W epsilon r and V epsilon r are bounded in H1 independently of epsilon, then we can conclude that V epsilon minus V0 is of order epsilon. Okay, so V epsilon minus V up will be of order epsilon, but then we have these terms that are of order epsilon. So we can just keep V0, and V0 is the solution of the initial problem, okay? Which was a reaction diffusion equation with Neumann or Robin boundary conditions on one boundary. And then, so we conclude that, and we are also able to conclude, so this is the convergence, as I said, of the penalized problem towards solution of the initial problem. And in the obstacle domain, okay, we are able to, if we show that the remainders are of order epsilon, then we will have this of order epsilon. And this means that there is a boundary layer in the neighborhood of the left boundary, and because theta is because theta is localized in the neighborhood of 0, if we are far from the boundary, we can also get a convergence of order epsilon to the limit solution far from the boundary, far from 0. So as I said in a previous article, we studied this problem in one dimension, but we studied it, we showed the convergence using explicit calculations and asymptotic, like by hand, let's say. And here we are. This is an alternative. We are going to see an alternative proof here, if we are able to bound the remainders using the boundary layer approach. And this will give a finer description, because in this article, for instance, there is no, we just studied what happens in the fluid domain. We hadn't convergence results in the obstacle. I mean, convergence order results. And yeah, so the utility of using the boundary layer is that we can extend it in high dimensions. So this will be the subject of the second part of today, because here I present calculations in one dimensions. As I said, so it's not, we don't need all this in one dimension because we can do explicit calculations, but the utility is that this approach can be extended in high dimensions, unlike the explicit calculations cannot, in general, be extended. So this was in reality the motivation for my for this course. So I was interested in this subject related to this convergence questions in fictitious domain penalization methods. Okay, so let's go back to our calculations. It's not finished yet. So if we are able to bound these reminders independently of epsilon, then we finished. But this is what we are going to do. And as yesterday, what we do is that we start with the equation satisfied by W epsilon and V epsilon. And this allows us to write equations on the remainders. So we obtain these equations with some left right-hand side that depends on W up and derivatives, etc. So we have these formulas. So hopefully here in the fluid we have 0. We find that this right-hand side is 0. And we have continuity at the interface. We have continuity of the solution and the derivative. And the boundary and the value of W epsilon r on the boundary 0, at 0, is 0. And this is because we did everything for that. We introduced correctors here in order to have a Dirichlet condition at 0. So what we need now, so we have the only right-hand side that is left is this obstacle, is the right-hand side related to the obstacle, r epsilon obst. And so we need to calculate all this. And as I said, here in one dimension, W tilde, the terms of the boundary layer depend only on Z, depend only on this boundary layer variable x over epsilon. And so this will simplify at the beginning calculations, etc. So we will write everything here and we develop, and because we have equations on W0, on the W0 tilde, etc., this also allows to simplify. There are terms that cancel out, and we end up with only these terms, okay? And what we want is only estimate. So, okay, we want to estimate these terms, knowing that, remember, we had found W tilde I were something, so it was either an exponential or Z times exponential minus Z, or sometimes Z squared. So it's a polynomial times in general. So it's a polynomial on Z times exponential minus Z. And this is bounded in R plus. So this allows us, for instance, to bound this term here. So we have some terms with theta. Okay? So when theta equal, when we have terms with theta, we have to be careful, because when you take the value at the boundary, for instance, you have 1. Let's say you can have some the value, for instance, of exponential minus Z at Z equal to 0 is 1, and so we don't want to have some term of order 1 over epsilon times theta times W tilde, okay? Because this will not be convergent. Yesterday, I think we hadn't terms with the theta, but here it seems we have terms with theta, and for these, it's important that we don't have terms of order 1 over epsilon. So maybe before, just let me go back. Maybe there were some terms of order 1 epsilon. But hopefully, for instance, here you see there is theta over epsilon to the power 3, and because it's theta here, this term is not good. Okay, so these terms, hopefully, it simplifies with maybe some derivatives, because we have some equation on W0 tilde, and so at the end, the terms that are multiplied by theta are not, there is no 1 over epsilon, and so this is bounded. So this is okay, we can bound it. And then we have some terms, epsilon times theta. This is also okay, this is bounded by C epsilon. These terms also are, okay, are good. And at the end, we have also terms theta prime. So when we have a theta prime or theta double prime times something, here there is no problem if it's divided by epsilon, for instance, because we know that, for instance, W0 is exponential x over epsilon. Remember, just let me explain this term. We saw it yesterday, W0 tilde exponential minus x over epsilon divided by epsilon. If it's multiplied by theta prime, then this will not be harmful because this term is 0 at in the neighborhood of 0. Okay? So this exponential cannot be equal to 1. So we are going to look only at what happens when x is bigger than delta, and this allows us to write that this is smaller than exponential minus delta over epsilon times power of epsilon, and this is an exponentially small term. This will not be harmful. And we have also some, because w tilde is a polynomial, this also will not be harmful. So when you replace z by x over epsilon, you can have some x over epsilon here also to some power, but then you will just say that x is smaller than 1, and then this is an exponential. Here, if you epsilon to the power L exponential minus delta over epsilon, this goes to 0 for L in Z. Okay, so this there is no problem for this. Anyway, so you have just to look at any terms here and show that they are bounded. So this is what we are able to do. We are able to bound this right-hand side on the obstacle independently of epsilon. And in reality, we are going to see that we will need more than that. So it will not be sufficient just to bound this right-hand side. And if you go back to the expression of this right-hand side, you will find that if we are far from this theta, this theta is localized near the boundary. So here in this part, we are able only to bound epsilon obst by a constant. But then if we are far from the boundary, you look at the expression and you see that the terms that are multiplied by theta will disappear because theta will be 0 far from 0, the boundary 0. And then there will be, the remaining term will be just some epsilon times something, okay? The terms that are not multiplied by theta or theta prime or theta double prime is this term. And this term is bounded by C epsilon. Okay, so far from the boundary, we have, so that we introduce here a delta. Delta is what we wrote here. So delta should be bigger than the support of our theta. Okay. Say here. So here we are able to bound by C, but then in this part, delta 1, we are able to bound by C times epsilon. Okay, so this is the only right-hand side we have in the equations. And now the objective is to deduce an estimate on the solution, on the remainders. And so it's as yesterday. The approach is the same, is that, well, the first thing that we can try is to multiply the equation by the solution, by itself, by the solution, and integrate by parts. But what happens here is that as for the convection diffusion equation we saw last time, the simple example, it was not sufficient to multiply by the solution, integrate by part. If you remember, in this case, we multiplied by the solution times exponential x. Depends on the signs. And here as well, if it doesn't work if we just multiply by the solution and integrate by part. So what we are going to do, and it will not work also by multiplying by exponential x in this case. So what we are going to do is that we are going to multiply by the solution, but with some weight. So we are going to take the equation on v epsilon r. And for v epsilon r, the equation is just minus v epsilon r double prime plus v epsilon equal 0. This is what we obtain for the equation on v epsilon r. So what we do is that we multiply by the solution times a weight p epsilon. For the moment, we don't fix p epsilon because we don't know what to take for the moment. So we just say, let's multiply by some weighted function by the solution times multiply by a certain weight. And we are going to do the same thing for the equation on w epsilon r. And then we will add the two equations and see what are the conditions that these weights should satisfy in order to be able to obtain some estimates. So, okay, just some comments on this. So you take the equation on v epsilon r. Let me just remind you of the equation we obtained. We have this on the fluid domain, which is 1, 2. You take this equation, you multiply it by v epsilon times p epsilon, and you integrate over the domain. And then you do some integration by part. Okay, so you do integration by part. You will have some boundary terms here. Again, so also contrary to the simple case we took, or for the convection diffusion case, for instance, we multiplied by the solution times an exponential, and there was no boundary terms. But this was because the solution was in H1 0. Here, because we have some interface, v epsilon is only, what we know is that v epsilon r is 0 at point 2. Okay? So we know that the remainder will be 0 at point 2, but it will not be, okay, what happens at the interface 1, there is interplay with the part that is happening in the obstacle. So here we don't have v epsilon r1 equal to 0. That's why we will have some boundary terms that will remain. Okay, but at the end you develop everything and you end up with this last equation where you have boundary terms. So you see here you have v epsilon r at point 1 and also v epsilon r prime at point 1 that will be present in the equation. Okay. Okay, so this is the equation, the first equation we obtain when we multiply this by v epsilon r times some weight. So we are going to, so this means that we will introduce some weights. We will call p epsilon the weight on in the fluid domain, and here we will call it q epsilon. And for q epsilon, it's the same thing. We start with the equation on w epsilon. So the equation on w epsilon r comes from the obstacle part. Let me just write the equation on w epsilon r. Epsilon r double prime. You take this equation and you take chi equal 1. Plus alpha w epsilon r Okay, so the equation on the remainders in W epsilon R is this equals some right-hand side, which we called R epsilon obst. Okay, so this was the equation, okay, on W epsilon R. So we start from here, we multiply by epsilon, W epsilon R times a function Q epsilon that we don't know for the moment, okay? And we integrate by parts, so you do the same things. And again, you will have some terms on the boundary at the interface 1, because all we know is that W epsilon R at 0 is 0. But then at the interface, these are connected. We don't have the value at 1. We only know that then we have continuity at 1, and also for the derivative. This is what we know. But we don't have the value at 1. Okay, so when we arrive here, so we have two equations. This is on W epsilon R. And then we sum the two equations. Okay, when we sum the two equations, so because we don't control, well, we don't have a knowledge on these values at the boundary, we are going to, first condition that we are going to put on the weights is to get rid of this boundary. Okay, I cannot control this term, neither this term, so I'm going to choose, so we have to add this with the other one, it was before. And because I cannot control what happens on the boundary, I will impose that these boundary terms vanish. And this gives that P epsilon, so this gives a condition on the weights. The first condition on the weight is that P epsilon is continuous, so P epsilon is equal to Q epsilon at the interface. But then for the derivative, it's not continuous. You have some jump in the derivatives, okay? For these weight functions. And then we end up with an equation with no boundary terms. This is what you see here. This is an equation with no boundary terms because we imposed this condition, for instance, on the boundary, on the weights. And then remember, what we want is to estimate the remainders in the H1 norm. So we want, we don't want these integrals. We want, in reality, V epsilon R, the H1 norm of V epsilon R and the W epsilon R, etc. And so for the exponential, if you remember, we had some integrals like that. We had some exponential x here, but then we used the fact that exponential x is bigger than 1 if we are in the domain 0, 1. And so this allowed us to to obtain estimates on the integrals that interest us, that are the norms in L2 of the derivative, for instance. So here is the same thing. What we are going to do is that we are going to assume there exists P epsilon and Q epsilon such that first we have this condition, okay? This should be valid because we want to get rid of the boundary conditions. And then we will assume that, because we want here to obtain some, we want to obtain these integrals, for instance, on the derivative, let's say. So let's assume also that these weights are positive. So we assume that P epsilon is strictly positive at 0 and also Q epsilon. So this will allow us here to minor this, to have an inequality that says that, this beta in this integral is less than this integral. Okay? Then here, okay, because we are going to use the Poincare inequality afterwards, that will be valid, we will only impose that this is positive. So it means that this integral will be positive because everything is positive. Again, also for this integral, we are going to assume that these terms are positive. for instance, and we are going here to be, we are going to need this estimate on Q epsilon. So we will assume that Q epsilon is bounded near 0 and is of order 1 over epsilon on delta 1. So if we assume all these things, then all this, the left-hand side is bigger than this, okay? Because this is positive, and these we use the fact that P epsilon is bigger than beta, which is strictly positive. And on the right-hand side, we use some inequalities, okay? So on the right-hand side, we have R epsilon times, okay? This integral here, we use Cauchy-Schwarz to say that it's smaller than this product. Then this L2 norm of the R epsilon, Q epsilon, we just split it into, okay, maybe there is some constant here. Oh no, it's okay. This is the norm in L201, so it's the sum of the norm in 0 delta plus the integral on delta 1. And then we use this inequality, and then we use the estimates that we have. So remember, we have, that's why we needed this to be, we have R epsilon ops on 0 delta, which is smaller than C, but then, and on delta 1, it's smaller than C times epsilon, and Q epsilon is bounded on 0 delta and is of order 1 over epsilon on delta 1, and which means that we are able here to have something, just a constant, because we have C times C, or C epsilon times C over epsilon. Okay, so all this will be bounded independently of epsilon. And then we have W epsilon R. So we end up with a constant times W epsilon R L2. And as I said, I said that, so W epsilon R is not in H10. Okay, it's 0 at the boundary 0, but at point 1 we don't know. But Poincare inequality works also when you have, okay, we can show it, it works also in 1D, and if you have only the value at 0 that is 0 at one of the endpoints of your domain. So we are able to use Poincare inequality. So this is smaller than constant times W epsilon R prime L2. And then on the left, what you have is the L2 norm of the epsilon R prime and the L2 norm of the W epsilon R prime. And then you use here Young inequality, and we end up with this. Okay, so finally, okay, if we end up with this, it means that this norm L2 is bounded. And also for epsilon R, we can use the Poincare inequality because the value at 2 is 0. So at the end, what we end up with is that the H1 norm of the remainders are indeed bounded by a constant independently of epsilon. Okay, so sorry, but this is okay if we assume that we can find weights. Okay, this is we didn't treat yet. So if we assume that these weights exist, so if P epsilon and Q epsilon exist that satisfy all these conditions, then we finished our proof of the convergence. So which means that now we reduced the convergence of the method, the transaction method, to the existence of these weight functions that satisfy some conditions. And so now this is what we are going to consider. We are going to show that we can construct these these weights in such a way that they satisfy these conditions. And I suggest maybe that we do that in the second part. So let's take a small break before continuing this proof. Thank you. So now the objective is to find these weights, okay, these suitable weight functions that satisfy the conditions we obtained before. And yeah, let me just go back to these conditions. So the conditions were some conditions at the interface, and then these conditions of positivity, and also the solution of some these conditions also on these equations and these estimates. And just so in order to get rid of the constant here, these 1/1/2, etc., are not very important, and because we also know that alpha that we have in the boundary conditions for Robin boundary conditions is positive, we can simplify the conditions we obtained. So we are going to look to weight functions that satisfy these conditions. Okay. So which means that, so here you have some equation on obstacle domain on Q epsilon. So in reality what we obtained is an equation on Q epsilon, an equation on P epsilon, then some interface conditions, transmission conditions, and then we need also some positivity and these estimates. So just in reality, so we don't need, we need this to be positive. And so we speak about super solutions. So we are not looking for a solution to some equation equals 0. We just need this to be positive. So what we are looking for are super solutions, what we call the super solutions. And so this is if we find these weight function that satisfy these conditions, then it will satisfy the conditions that we had before with some constant, etc. So this is not a problem. And first, let's so this is another problem we obtained. So our first problem was, I mean, our initial problem was we had some equation on V epsilon. We had some F here, and then we have some equation on W epsilon, and we had some transmission conditions. This is a different equation. So if you look at what are the difference for P, it's the same. I mean, if we don't look at the second right hand side, it's of the form minus P double prime plus P. This is the same equation as for V. While what is the difference for Q? So for W, we had an equation like that. So we had minus W epsilon plus W epsilon if we get rid of the alpha, and here we had minus, here we have minus W over epsilon, and here, so the difference is that now we have a plus sign. Okay, so the equation is different, and if you remember what I said on this convection diffusion equation and the boundary layer, where is the boundary layer? So if you have this equation with a minus sign, then the boundary layer is at 0. But now the equation that we have on Q is with a plus sign. So we expect to have a boundary layer at 1. Okay, so this is a different problem. So that's what we really will see. So I will show maybe some simulation, some figures, but maybe before. We can show that this problem is linked to a dual problem. So this is the equation we get. We can try to write this in a variational form. And if we want to write it in a variational form, so we take a phi in H10, we multiply and integrate by part. We take into account these conditions. And if you do that, if you do these calculations, you end up with an equation of this form. Okay, we end up with this variational formula, and it's a variational formula that is quite similar to the one we had for the initial problem, except that, so for the initial problem what we had here was minus So if you multiply by phi, you will have the integral of minus w phi. While here, what you have is the integral of the solution times phi prime. And so this is a different equation in a conservative form. So we talk about a dual problem. It's a dual problem for our initial problem because we have the advection term in a conservative form. We will see that also in a higher dimension. Anyway, we have existence uniqueness for this problem if we specify the right-hand side. Okay, so before constructing this, let me show you. If we solve this equation, let's say we solve this equation with b is equal to 0 and a equal to 0. And let's say we impose. So let's say we solve this equation. So let's say we take a right-hand side equal to 0, and we impose, for instance, that the value is 1 here and 1 here. So this is just to understand how this equation, how the solution behaves, because you see here you have some transmission, some jump in the derivative. So we want to understand how this works in order to construct these super solutions. So let me show you some figures here. So what I plotted here, this is the solution of the equations on the weight. So if I solve the equation equal to 0 and imposing the value equal to 1 on 0 and 2, at 0 and 2. And here, so what is plotted here, for instance, red is, let's say, 10 minus epsilon for different values of epsilon. So the red is 10 minus 1, 10 minus, maybe this is, okay, we change here epsilon. And what we notice is that, you see you have, well, this will not be converged, of course, with respect to epsilon. In reality, what we notice is that value at 1 will be of order 1 over epsilon. And on the left, it's q epsilon. Q epsilon will be, it seems that it will also be of order 1 epsilon. This was one of the conditions that we should satisfy. And so this gives us some insights to construct the solutions. So we can, for instance, assume that, and here the value is 1 because I imposed the equal to 1. Okay, so this gives us an idea to construct suitable super solutions. So let's come back. What we are going to do is that we are going to take q epsilon equal 1 plus some boundary term here, but that is divergent, because this is what we notice when we solve, for instance, the equation. And because we only need super solutions, in this one-dimensional case, we can construct this. So what we are going to take, we take q epsilon is 1, so it's 1 plus a boundary term which is of order 1 over epsilon, which will be localized here at 1. So which means that I need to take some exponential of minus the distance to 1, and the distance to 1 is 1 minus x, and that's why we take this formula. Okay, so this is a boundary layer term, exponential minus the distance over epsilon. And because we found that there is some divergence at the interface, we take 1 over epsilon. And then this is, we are in 1D, let's say we can construct, this is just to have the positivity, etc. So we add some constant here that depends on epsilon. And we can show that this is bigger than this, and this tends to 1. So which means for small value of epsilon, this will be positive. So this is first condition that we want to satisfy. And then when you calculate this formula, we find that it will be equal to q epsilon. I will explain after why so this works. So we find this, And because Q epsilon is positive, we also find that this is a super solution to our problem. And then what we do, so now we fixed Q epsilon, and for P epsilon what we are going to do is just, we are going to take something that is, so P epsilon should satisfy two conditions on the value at 1 and on the derivative at the interface. And we are going just to take some affine function. So we take an affine function, and because we want to satisfy the conditions at one end of the derivative, we take this formula. And so what we should verify is just that P epsilon should be also should stay positive. So we should here there is an error. So when we calculate P epsilon double prime plus P epsilon, we find that it's not equal to 0, it's equal to P epsilon, because this is affine. So minus P epsilon double prime plus P epsilon will be equal to P epsilon. But then P epsilon, when we calculate the value at 2, when you calculate the value of P epsilon at 2 and at 1, you find this is, we take an affine function, we calculate the value at 2, we find that it is positive for epsilon small enough. And at 1 also it's positive because Q is positive. So finally, the conditions that remain to be satisfied are condition of the estimate on Q. And this we obtain just by by inequalities, by looking at what happens on 0 delta near the boundary 0, where we can use these inequalities. And yeah, so here we want to have a Q that is bounded. And if we are far from boundary, we are able to use this inequality on the exponential of x minus 1. And then if we are in this part near 1, we use the fact that the exponential of x minus 1 is smaller than 1, because x minus 1 is smaller than 0. Okay? So when we are at the boundary, we cannot get rid of this 1 over epsilon, but that's why we needed this, this estimate. So here we find the conditions that we want. If I come back here to the conditions that the weights should satisfy, we are able in this one-dimensional case to construct explicitly these weight functions. And with that, this means that you go back to what we did before. We have the boundedness of the remainders, and this implies the convergence. Okay, so we're done with this. Yeah, just wanted to show you this construction. So this, what I showed you here, this was solving the equation on P epsilon equal to 0 and this equal to 0. But we don't need we just need super solutions. And the construction I showed you, it will be, so you see here, this is not affine. The solution P epsilon is not affine because it solves minus P double prime plus P equal 0. And what we constructed is this. It's an approximation, let's say, of the solution if we take equal to 0. So we have the same behavior. When we take epsilon goes to 0, we have this 1 over epsilon here with some boundary layer near the interface 1 on the left. And here it's sufficient to take something affine, and we end up with something with a value at 2 which is positive, etc. Okay, so we are done with the penalized problem in the one-dimensional case. So there were some differences with the Dirichlet conditions, especially in the estimates. Okay, so it was not sufficient just to multiply by the remainders and integrate by parts. We needed these weights. And now what I suggest is to show you how we can extend this in higher dimensions, because the utility of boundary layers is that we can use them in higher dimensions. You can see that in this book. where it is detailed for Dirichlet boundary conditions. And so the idea, what we did is adapt what was done in Dirichlet conditions for other kind of boundary conditions, Neumann or Robin boundary conditions here. And as we saw, there are differences. There are some big differences related to the location of the boundary layer and related to the obtention of the estimate. Okay, so I suggest to show you how briefly how we extend that this approach in higher dimension. So we come back to our problem. You remember, in high dimension, the problem we take is this one. Okay, so now I come back to the higher dimensional case. Let's say here we consider D equal dimension 2. And so I consider this model problem minus Laplacian U plus U equal F with this Neumann-Robin boundary condition. And as I said before, the penalization we consider is this. So this is a generalization of the one-dimensional case. We take the boundary condition and we put it, we force that term in the complementary domain. Okay, and we are going to show, I'm just going to show how the boundary layer approach works in higher dimension. So we are using the boundary layer approach to some regularity, so assume regularity on the domains, etc. And so we assume some regularity, and then the approach is the same. We split the problem into what happens in the fluid domain and then the obstacle, and then we have transmission conditions. This is equivalent to our initial problem. And for this problem, we are also able to show the existence of uniqueness using some results for non-coercive problems, because we have here a non-coercive elliptic problem. Okay, so let me explain the method. So the same thing, we consider an ansatz on the solution of the same form, and let me just explain, as I did here for the location of the boundary layer. Let's just look at what happens in dimension 2, for instance. Okay, so as I said, when we look formally at what happens, you find that for chi equal 1 in the obstacle domain, you will have at the limit this equation, gradient u, let's say 0.n plus alpha u0 equal j. This is what will be satisfied in the complementary domain. So this is u, and this is omega, small omega, and this is bigger omega. And this is a first order partial differential equation. So in general, it depends on this vector here. You have the right to impose boundary conditions only on some parts of the boundary. And because you have here n will be an extension of the normal vector on the initial domain. So this is, if you impose the value, if we impose u0 equal, and this is what we want, okay? We want to we want to u epsilon to converge to the solution of the initial problem, and then by continuity we want this will be in fact W0. Let me call it W0 bar. This will be the limit problem, and what we want is W0 bar equal U on the boundary of the initial problem, and this is in W. And just to simplify the calculations, in the one-dimensional case, because it's we had here the normal, we took 1, 2, so the normal, the outward normal on this boundary was just -1, and we extended this just by a constant, so it was -1 everywhere, and so on this part it was also it was going outwards at this point. And in the one-dimensional case, the limit problem was this equation with the value that is specified at this boundary, and then we had a boundary layer here. So in 2 dimensions, it will depend on the, let's say this is n tilde, and then we extend it, we called n the extension. And so imagine here at this point you have n. Here n is the extension. So these are partial differential equations of order 1. So it depends on the conditions we take, but in general it will pose if you impose the value on the boundaries that are such that this vector is going outward of your boundary. So which means that to simplify the calculation, we are going to assume this is n, this is the elliptic of n tilde. And if I call this n omega, what I call n omega is the normal or nu, just to, so nu omega is the outward normal vector to the bigger domain. We are going to assume that this condition, just to simplify the equation, so we are going to assume that the scalar product between n and nu omega is positive in order to have an outward vector on this boundary and to have a well-posed problem just by imposing the value of W0 bar on this boundary. Okay, so this is for some technical reasons. We assume that. Okay, and then so when we do that, it means that we will have a boundary layer. So this will be well-posed, so will have a solution, and then we don't have the guarantee that the value at this boundary will be 0, and so there will be a boundary layer. And so how we generalize the approach in 1 dimension? In 1 dimension, we had here x over epsilon. X in reality is the distance to the boundary where we have a boundary layer. So here, if we are in 2 dimensions, this will be replaced by phi x, where phi is the distance to the boundary. And assuming enough regularity, we have results that say that this is well defined in the neighborhood of this boundary. So because we are going to localize, this will be enough. Okay, we are going to be able to define the distance with a given regularity, and we are going to use a theta that will be only localized here on the boundary. Okay, theta equal 1 on a neighborhood of the boundary. And then it's the same expansion that we take, replacing x here by phi x over epsilon. And so because we have in the expansion for wx phi x over epsilon, we are going to introduce a variable z. And then we are going to need this formula of the gradient and the Laplacian of this function wx that depends on x and phi x over epsilon. Okay, so we are going to use, as in the 1 dimensional case, these formulas. And the approach then is the same. We introduce in the equation and identify the different terms corresponding to different powers of epsilon. Okay, I skip that. At the end, you obtain the equations on different profile terms, and we are able to solve them. Or at least what we should do is show that the problems are well posed with the suitable regularity. So yeah, we need to show the well posedness of the equations. Okay, sorry. So the first part is a formal resolution, and then we show that all the problems are well posed. And okay, this is exactly the same as before. And then we write as before. We look for a solution with some remainder terms, and the objective is to show that the remainders are bounded independently of epsilon. And for that, we write the equations on the remainders. As before, we have, it's just here that we are going to be on dimension 2, but we will have these types of equations in the obstacle domain, fluid domains, and with transmission conditions. And then we need to write the right-hand sides that are involved in these equations. So again, a lot of calculations that will simplify, hopefully, because of thanks to the equations that we have on the boundary layer terms. For instance, we will obtain, okay, this is the formula for the right-hand side, but then this will simplify, and the idea, as before, is to just try to estimate them, to see what happens when we have some the theta terms, and where there are derivative gradients or Laplacians of theta. As before, we show that this is bounded. Okay, we look at different terms. We show that they are bounded. Okay, so just I'm going a little. This is a work, a submitted work, and it will be available on archive soon, hopefully. So the details will be available to you if you search that. But I wanted just to explain the approach. It's generalizing what we obtain in one dimension. So finally, we obtain that this right-hand side is bounded if we are. If we are, I call this region where theta equal 1, w equal 1. No, where the support, let's say, of theta is w1. So the right-hand side will be bounded here, and then it is of order epsilon if we are here. If we are far from the boundary, it's of order epsilon. So this is the same result we had in one dimension. And the methodology is the same to obtain the estimates. It is not sufficient to multiply by the solution, so we multiply by weighted functions as before for the solution inside the fluid domain and that inside the obstacle. We sum the two equations, and we impose conditions on these weights. It's exactly as the one-dimensional case. We impose this to get rid of the boundary layer boundary terms, integral boundary terms, and then we end up with this equation. And again, we can see that if we impose all these conditions, that the weights are positive, and that these equations here, these expressions here are positive, plus the estimate on this Q epsilon, then we can do the same thing as in one dimension and obtain the boundness of the solution independently of epsilon. Okay. So now the question again is finding these suitable weights P epsilon and Q epsilon that satisfy all these conditions. And to do that, here it's more difficult than the one-dimensional case where we were able to express like to give an explicit expression of these weights. So here what we are going to do is so as we saw in before, when we solved like the equation and looked at the behavior, we found that there was some boundary layer at the interface. Okay, so here also the problem that we obtain for P epsilon and Q epsilon is related to the dual problem, and so instead of having a boundary layer here, we will have a boundary layer at this on this boundary with some and Q epsilon will also be of order 1 over epsilon on this interface. And so what we do, because we cannot construct explicitly these weights, is a formal boundary layer approach. So based on these numerical simulations, for instance, we can assume that the P epsilon can be decomposed. Let me just go here to explain what we do. So this is the equations that we want to solve. Okay, we want to find P epsilon and Q epsilon that satisfies this, for instance. We don't want to have it equal to 0, so it's sufficient that it's equal to something positive, also for Q. And based on these numerical simulations we did, we can assume this ansatz on the solution P epsilon Q epsilon. So as I said, there is a boundary layer that will be now near the boundary of the initial problem. And there will be also terms of order 1 epsilon. So we don't have convergence. So the difference with the ansatz for the solution of the initial problem, it was just orders from epsilon 0 to epsilon 2, etc. Here, we assume this decomposition. And the boundary will be also only localized in the obstacle domain. Okay, so we assume this and that. We do the same boundary layer approach as I presented. So we take this expression and introduce it in the equation. And let me go back to so we are able then to obtain some equations on P minus 1, etc. Let me just go back. Sorry for that. So when we do this approach, we find equations on P minus 1, P0, and also this Q bar 0, Q tilde 0, etc. With different, let's say, different degrees of freedom. So, for instance, this value is not fixed. We should find these values Q0 bar, gamma, etc. And so the idea is to take only these first terms, so order epsilon minus 1 and epsilon 0, and so take this as an approximate solution of the weights. And so we are going to take this approximation and introduce it into the equations on P epsilon and Q epsilon, and try to find try to tune the different degrees of freedom in order to satisfy all these conditions. And because here we are looking at order, if, for instance, if we want this to be positive, we are going just to impose that the dominant term is positive. And yeah, so I will not go into detail. So this will be available to you if you are interested. But at the end, so we are able to explain a construction for these weights also in high dimensions. And with that, we are able to show the boundness of the weight of the remainders independently of epsilon, and this concludes the convergence in higher dimensions as well. Okay, I think I'm with that. I am done. So for this last part, as you see, there are a lot of calculations, etc., for in this boundary layer approach. So I prefer to present the approach in 1D. But then all what I presented here can be extended in higher dimensions with some technicality. But yeah, so I hope that these lectures were useful for you. And do not hesitate if you have any questions to contact me. And with that, the lectures come to an end. And thank you for your attention.